in this system is 45 minutes. So if you're not refreshing within a 45-minute slot, your identity will go away. So essentially, this is the way the kind of like an overview of what the GHT is doing and how it works. Internally, there's a routing table inside there, which is each node keeps such a routing table, and it has its own identity, which is also a number in this big space where the other identities lie. And the idea is that each node couldn't keep a complete routing table because the complete routing table is in the millions of nodes, right? So because it's in the millions of nodes, you could not keep the complete table. So you keep a partial table on each node. And the trick is that you're building it in a way such that the closer, so you have an identity. Each node has an identity in the routing table and has an identity in the search space, which is the same space as we store identities which we map to IP port pairs. And the closer we are to ourselves, the more we know, the more nodes we know. So that means, for instance, suppose you have a long bit string and use the first bit there is a 0 for your case. Then you don't know more than at most 8 nodes that has a 1 bit there. And as you have more and more of your own identity, as more and more, as you get a larger and larger prefix in common with the node, you'll gradually know more and more nodes close to yourself. So there's it's based on the bit strings of these identities. I'm not going to cover it too much, but the effect is that the closer we are, I mean, we know more about our neighbors, so to speak, in the distance metric than we know about people who are a long way from us. And this is why we can use this recursion scheme where we can ask others who has other parts of the partial routing table and ask them what they know. And if they're closer to the target, they know more because they have more of the prefix in common than we have. So that is more or less how the kind of like a little bit about how it works. The Erlang implementation I've written has this structure in general. Let's see if I have a mouse. So these diamonds are processes in the system. So there are 4 processes in the system itself, which are the network subsystem, the state subsystem that tracks the routing table, a store which tracks identities from others, and a tracker which track our identities in the table so we can refresh them. Since this is Erlang, there's a specific process called the supervisor up here who makes sure that if any of these dies, we restart them from a safe state. So this is a standard thing in Erlang that you are trying to build robustness by that. Different internal clients in the system, they can do queries out, and they do that by manipulating either the store, the tracker, or directly the network. Out here we have the internet, and the internet communicates with the network part of the system. So there's UDP packets going back and forth between these two guys. The things in boxes are modules. So we have different modules in the system. So the protocol coder is tied directly to the network stack, whereas the random subsystem here that handles the random numbers is shared by multiple things. And the same for this module down here, which handles time in the system in general. One of the things is that the state here keeps the partial routing table inside here, and the state metadata is the thing that is responsible for refreshing nodes that we know in the routing table. So the problem with the routing table is that it is dynamic, right? At a certain time, a node might be added to the network, or a node might disappear from the network. And in order to handle that, we need some kind of metadata that keeps track and periodically refreshes things, and that is the state metadata that does that. And everything here is then governed by the state process itself, which then keeps that routing table state inside the system. So this is the overview. You have 4 processes in order to handle this. That is actually enough. So what is the motivation here? Well, there's millions of nodes, so the code better be correct. One of the problems you have is if you have a very large system like this, is the question of how do you do software upgrade. I mean, say you find a bug and you fix the bug in the system, then the problem is that that particular bug, I mean, it's in the system now, and you make a new patch and you upload your new patch, and not everyone upgrades, right? So the problem is that there are certain bugs that might persist forever in your system because it's so large. It's not possible to have everybody patch at a certain point in time. So that is one of the reasons why you really want correctness. You want to try to minimize the risk that there's any kind of error going on in here. And then also the code is somewhat tricky, so you better get it correct. So this is kind of like, why do extensive testing on this? Well, this is the motivation. So quick check is a method that was invented by a guy named Cohen Claassen and John Hughes back in 1999. And the way it works is that they observed one very important thing, which is that if you write unit tests and you get to a certain point in your software, it doesn't scale anymore because it's human effort to write unit tests. And the problem is that once you have different kind of unit tests, you can combine them into new tests. And this means that you get a multiplicative way of doing things, and that means that the number of test cases you have, they explode, and they explode exponentially if you want to cover every kind of interaction. So this is a problem because it's very hard work to maintain a large set of unit tests. So they thought about this, and they figured out that, well, this is one problem. The other problem is that writing unit tests is some of the most boring thing you can do. So they decided to make it fun to write test cases. And the way you do that is don't write the test cases, but generate them automatically. So how would you go about generating tests automatically? Well, the way QuickCheck does it is it says, well, we come up with some kind of property, which is a mathematical property very often, that the system we want the system to have. So we have some system under test, and we want to check that it has this particular property. So what we can do is we can generate random inputs to the system under test. And then verify under these very random inputs we just generated, well, then the system has the properties we want. And the goal here is to try to make the system break and find something where we break the property, right? Because that means we have a bug and we can fix it. The thing is that coming up with good properties tends to be non-trivial. This is where you need a certain kind of experience in order to do it. And the more you do it, the easier it gets to come up with good properties for the system. The thing that people usually start doing when they think about this is, so the problem is, don't you just re-implement the property? I mean, don't you just re-implement the system you just built in the property? And the goal is to avoid doing that. So what you want to have is you want to have simple properties that does not necessarily capture all of what the system is trying to do, but just capture the major parts of what the system is trying to do. And the hope is then that if you break one of those simpler properties, which is essentially simpler than the system you are implementing, if you break one of those properties, then you actually find bugs in the system. So in a certain sense, it's not a question of formally proving that this system is entirely correct. It is a way to, it's a way to find bugs in your code efficiently. And that is the goal. And this is why I call it semi-formal, because it's not really formal. It's just a very powerful tool for finding bugs in the code base. The key power of QuickCheck is that once you have a counterexample for your properties, or once you know something that isn't true because of something, it employs what is called a shrinking policy. So it tries to minimize that test case down until it finds a simpler test case that it can then present you. And this is powerful because it means that you automatically get simple test cases, even though the error might occur in a very complex fashion. So I have had test cases where you have 200 something steps in order to produce it, but after shrinking, it's 6 steps to produce it. And 200 something is impossible to actually figure out what is wrong. But 6 steps, it's easy, and it's better yet because all of those steps, you know that they are related to the bug. If the system were able to remove one of the steps, and then it would have a smaller test case. So it's really good at minimizing test cases. It's not necessarily the minimal one, but it's close. So how do you do it? Well, as I said, a metric. In order to be a metric, you need three properties. You need a property of reflexivity, you need a property of symmetry, and you need the triangle inequality to hold. And here I'm going to focus on symmetry just to give you an example. So symmetry says that if I have two identities x and y, well, then the distance from x to y better be the same as the distance from y to x. So this is a property of being a metric. And here's how you would formulate it in quick check. So you say, well, for all pairs x, y, where we generate, this identity here is a generator that generates a random identity, and we generate a pair of those, well, then we can ask, are the x to y distance the same as the y to x distance? And once you run this, it'll push out, it'll generate random identities and do this. And in this case, I ran 100 test cases, which take like 2 milliseconds. And then it has verified this. And of course, inside the full model, you would also say verify reflexivity and the triangle inequality and other stuff. So this is kind of like an example of how you verify simple properties in quick check. But that isn't really gonna cut it for a complete DHT. So stateless quick check models, which is what I just showed you, is not enough. So you need to employ more advanced tooling. And the more advanced tooling is called stateful quick check models. So now in this case, we always generate inputs, and we have no state between, say, running this once and running it again. What we really want is we want to be able to say, if I have executed, say, a ping command, I expect that later on a pong comes in, or something like that. So I need to know that at that point in time I have a ping outstanding on the network wire, such that I can receive it later on. And this is what leads you to the idea of building stateful models. So the idea of a stateful model is that you have some states on the model, M0, then you generate some command C0, and you get into another state. So you do a state transition into M1. And then you generate another command C1, you do a state transition into M2, and now you build up a stateful model where you transition between states. So what you're generating in this case is that you're generating, when you're sitting in state M0, you're looking at what are the possible commands I can generate in state M0, and that might not be everyone. There's a precondition here that might say, well, you can only generate in M0, which is the initial state, I might only be able to generate some kind of open the file or init the system thing. Then once I generate a command, I have to generate some inputs to the command, because in this case the command might be generate a ping. Okay, so what are the peer I want to contact, and what is what is the peer I want to contact in that case? So I have to generate the command, I have to generate its inputs. Once I have that, I also have a next state transition function in the system, so I can say what is the M1 state. So now I essentially build a model based on that concept, where I can generate commands, I can generate inputs to commands, and I can move between states like this. So now I have a trace, a state model trace state chain that I have built up. And this slide, I think I said most of it, yeah. So essentially what you do is you generate a random command, you generate inputs for that command, then you actually re-verify another precondition that the inputs are also valid, because there are certain situations where given a command, given certain inputs, they're not valid. And then you repeat this state transition until you have a sizable chain. And sizable chain in this case is something like 50 commands to 300, 400 commands. Something along that size. So once you have that, then you run the thing against the real system. So down here we have S0, which is the state of the system under test. and we run the same Z0 command against that one, the one we just generated. And the P0 here is then a post-condition verification. So now we run a step and we verify that the step matches our model expectation. And run another step, checks that it verifies, and then that it matches its transition, and so on and so forth. So the idea is now we have a stateful model, and it's very powerful because it allows us to say things we couldn't say before. Like we can say, if I'm trying to verify, say, a hash table, I can have a state that says what are the keys in the hash table, which means that I can start saying stuff like, if I look up this key, it better be there, and if I look up this key, it better not be there, because I know what the internal state of the system is. And I need this in order to handle this thing, because there's a lot of state going on in the internal processes in this system, and I have to handle those. So I need stateful models in order to do that. So the thing is that also here there's another important point about why do this, and the point is that once you have a stateful model, it is usually tighter in the sense that it is closer to the system under test, and that means that it is easier to find bugs, and the bugs you find are better and easier to actually work with, because you know more about what was the expectation of the underlying system. But it turns out that just using stateful models is not enough, because now we have, I mean, if we go up here to the overview, somewhere like this, we have like 4 or 5 processes in here, and we have a lot of different, modules, and we're trying to build a stateful model for all of these. And that is going to break down, because that stateful model will be so big that you cannot really understand it and cope with it. So there's a trick in Erlang Quick Check that is primarily built by Ulf Norell, who did ACTA as well. And the thing is that what he does is, well, rather than having one big model, let us split the stateful model into several components. So the idea is that you build a component for each module in your system, and then that module calls other modules. So you mock those other modules that it calls, meaning that now I can isolate a module. And by mocking it, I essentially isolate it from the rest of the system. The thing is now that once I do that, I have a set of isolated small state machines, one for each module in the system, and I then can cluster those together by recombining them into a full model. So this allows me to define the system by essentially isolating each module on its own, like the routing table module. I can say, let me build a correctness test for that, and then later on put it inside another module by clustering these underlying state machines together. So what you do is you do this by mocking, and there's a mocking system built into Erlang Quick Check for doing this. The thing is that whenever a system then calls out to another module, we say, well, this is an expectation of the mock. So we expect that there's a call out to this underlying subsystem. And then the response we send back is generated randomly, because we can do that. So in reality, we are now isolating the system and we're generating the response value. So we might say, well, we are here, we expect this call to be made, and once that call is made, what is the appropriate response? Well, it's either true or false or something like that. We just generate a random response in. And since we know what the response is, we are able to use this in order to know what the model should do later on with that response. There's also a possibility of doing model internal transitions here, which then further modularizes our components, and it allows us to do a lot of things where you can factor out commonalities in your state machines. So really you are starting programming at the model level and programming at the state machine level. And finally, there's a way to simulate the fact that you might have a call that blocks. And this is also necessary, because say I'm a client and I'm calling into the system with a ping. Well, that client is blocked until a pong comes back or a timeout happens. So in order to handle this, we need to have a way to say in the model that I'm making this call and now the call is blocking. And there's support for this in Erlang Quick Check as well. And the way it's done is via some clever continuation stuff. So essentially, you are wrapping up the rest of your. When the block happens, you take the rest of the operation as a continuation. You save that in a separate place, and then when the unblock happens, you splice in that continuation stack back into the current trace. So it's clever. It's really clever, and it allows you. The gist of it is that it allows you to handle multiple processes calling into the system and being blocked on the system, because you can model blocking processes with this. I have a simplified example of what they look like, these test cases. So this is the state system has a routing table lookup, and here we have essentially an identity, and we want num sum in nodes close to that identity. So this up here defines in the model in the test specification says basically, well, if you want to execute this closest to command, well, you're just going to call the real system's closest to command. So this is kind of like the command itself we can generate. The precondition for doing this is it has to be we must be in some state S which is initialized. So we're not allowed to do this closest to call unless the state engine has been initialized. So one of the first things the state system will do is it'll initialize the states, the distributed hash tables, routing table state system, and then it'll be in an initialized state. Then we have to generate some parameters. We have to generate the identity and the num up here. So how do we do that? Well, we supply some random identity and some random natural number. In particular, we can supply 0 here. So you can actually ask for the 0 closest to this one, right? That is a limit case. Then you have, this is a call out specification. It essentially says how the mocking system works. So it says so that, well, when you call in with this ID and num, I expect that there is a call to this routing meta system, and we're asking for neighbors down there, and we're asking for ID num, and this is just a dummy variable. So this is what we expect the mock to have in its callout, and we expect it to return. Then our generated return is a list of peers. So this is a generator, this part here, that generates a random list of peers that we give back. So now that is bound to the NS thing here, and then we say that the callout sequence returns the NS. So this means that the post condition of this thing is that it expects the list of peers that we just generated by calling into the subsystem through mocking is exactly the response we want for this closest to call in this case. But this, what this thing has done is that we have this state process that has some things around it. Inside that, there's a routing table, which we actually mocked out. And the only thing we're testing here is that our state process is doing the right thing under the assumption that the underlying routing table is doing the right thing. There's no internal state transition here, so I don't have a way to essentially transition from this state. I mean, S is the same as it were that when I started. And I looked in the code if I could find something that was easy enough to kind of explain in one slide that had a state transition, but I really couldn't find it. Many of the other cases are way more complicated than this one. So I just wanted to give you a feel for how what they look like, these things you write. So the global arch of doing this, how do you then do it? Well, the idea is build a universe around the client. So there's millions of nodes out there, so simulate millions of nodes, right? You don't want to run millions of nodes because that would be very expensive in your AWS credit. So you don't want to actually run a million of nodes. You want to simulate them. And the insight is that you don't have to simulate them all. You only have to simulate those you communicate with in this particular test case, which isn't all of them. It's very often like 5 nodes you have to simulate. So this makes it way easier. The next insight is the universe you simulate should be the worst ever, right? Rather than building a universe that behaves like normal universes behave, you want a universe that behaves really badly, like sending in wrong data. If you call out to a file system, it returns error E again or something nasty, right? If you make a query out, that query might go well, or it might time out, or the network socket might have an error because the socket is down or the network is lost. So you just encode all of these possibilities, and then you tune the internal system such that it is very often the case that the uncommon cases happen. So basically the normal operation is actually the one that is the most uncommon in the test case, and all the exceptional cases are the ones that are most common in the test case. By switching it around like this, you make sure that you hit all the nasty cases that people forget when they write code, right? And then there's another trick. Rather than using the large set of a 256-bit identity space, we just cut it down to 7-bit. So now I can at most have 127 nodes in there, and that means all the corner cases where you have collisions and nodes, they happen all the time. So that forces me to actually handle those cases right, because now I've made it simpler. And of course, when you then compile it for production, you just move 7 to 256. So this is another trick. Simplify the production system while you're testing it, and then open it up for the full thing when you're really doing things. So as I said, when you generate test cases, you want to tune them. You want to generate all the nasty cases. You don't want to generate the cases in your generated tests that are the common ones, because if you just use the system, you will be traversing that code path all the time. What you want to do is you want to force the system to do things that are not that common, right? So if you know a bit about the common cases that usually go wrong in such systems, you can really tune your heuristics such that it tends to find bugs very, very quickly. The goal here is, and I want to stress this, the goal is to find bugs. It's not to prove that the code is correct. Dijkstra famously said that something to the same extent at a certain point, that you can not prove the absence of bugs, essentially, that there's no way by which you can be sure that there are no bugs in your code. Even if you did a proof in some kind of proof assistant, then, I mean, your specification might be wrong. So there's always a boundary you can keep pushing. So here the goal is generate some test cases that are very likely to hit bugs in the system by being nasty to the system. So, well, what do you do? Well, the possible commands you can generate in such a model are all the commands that can be issued by a client inside that want to call out into the hash table. So that is kind of ping a certain node, or store this identity out in the table, or look for this identity in the outer table. And it's important to note that client commands can block. If I ping a node, then I'm blocked as a client until the answer for that ping comes back. So I have to handle that by model those as block-unblock commands in the system. And then the other kind of commands that can happen is that the universe can actually make a request at our node, right? So it can send a request into our node, and then we have to respond back to the universe. So there's commands we can generate as a client that calls into the hash table, and there's commands that the universe can generate towards us as a node in the world, in the hash table. So there's a bit more commands than just the commands that are the commands you can call into the system. So now we come into tricks. One of the problems in this system is that it has a randomness. There's several places in this code where you're pulling out a random integer. And the way you need to handle that is by mocking the randomness. And the reason you need to do it is that essentially what you're looking at here is that you have a two-party linear type system. In the sense that in a linear type system, you have a concept of choice, and there are two kinds of choice in this system. There's choice I do, and there's choice somebody else does. In this case, the model can pick among, say, several commands, or it can pick among several inputs to certain commands, and it's a choice that the model makes. But then the system under test might make choices as well, depending on what I put into it. And that is choice I have no control over. So for instance, if I do this, I generate a command that then forces the model to do a random call to the random system. Well, then the system under test is making a random choice over which I have no direct control. So here, by mocking the randomness, I can move the randomness into the model. So now I have the choice of what random value we return. So now I generate I just don't use the normal random number generator in the system. I have a random number generator myself. And then I use that one so I can predict what it is going to push back into the system. And now I have the control over the whole thing because I turned it around. And this is a very common trick you have to use in these systems in order to prove them correct. Because there's a lot of cases where the system under test have certain choices, and trying to model your system by allowing the thing to have certain multiple choices is usually very, very, very hard and sometimes totally impossible. So the trick is that you essentially mock that thing, move it into the model, and then you make the informed choice about what the underlying system should do in that case. So this trick kind of solved everything I had with randomness in the system, because there's no randomness anymore. I made it into explicit deterministic things which I control. And that leads me to the other thing, and this is perhaps the thing I see most of the time in the real world, no pun intended, which is time handling. So in systems in general, people are very bad at handling time. And the thing you should think about is that time should really be modeled purely functionally. So what you do is you say, well, there's a point in time, which we can call now, and we inject that into the call, and the system itself is never ever going to ask for the time from there on out. We say, we take the timestamp, and then we tell the system, the time is now this point in time, please do your stuff with that information. And it's the right way of looking at it, because time is what I call epsilon relative anyway. I mean, if you inside your system take a snapshot of time at a certain point, well, when the next instruction executes, we have already moved an epsilon in time. So the point is that time is always lagging behind in every system anyway. So you really want to model your system such that it is a catch-up model. It knows what the time is currently, and then it gets a point that says, oh, now the time is here. Okay, fine, so I have to catch up to that point. But while it's catching up, time is still moving a little bit, right? So now the time is actually an epsilon above that. But by building your system with this catch-up trick in mind, it's usually the case that you get better systems. I see very many systems that are modal in this, that they have a catch-up mode and an operating mode. So when they start up and they are behind, they start with the catch-up mode, and then they keep on being in that until they hit the, oh, now I'm caught up, so I go into operating mode. But if you write your code such that it is always catching up, you don't need the operating mode anymore. So you can get rid of that modal construction in your language. So what you do here is you write your time handling like this inside the system. So time is handled like this inside this model and inside the system under test. And then what you do is you say, well, let me then build a model of Erlang's timing constructs. So if I set a timer, it's a model that actually has the timer, and I'm mocking the real timing calls in the system. So again, I'm moving time from something that is controlled by the system to something that is controlled by the model. And I have a specific call in the model that says advance time from here to there. So now I control when time is actually stepping forward. And that allows me to find some really nasty bugs in and around time. Because I can have cases where something happens and something happens at the same time. Precisely at the same time, when nothing was in between. And that is not possible in the real world, but checking for it is nice. So this is a really good trick. Inject time and handle time purely functionally. It simplifies so much code. And once this project, I started doing it for real. And every project I've written since uses this model because it's so much easier. So what have I modeled? Almost everything. The only thing that is not currently modeled is the search system that recurses when it requests something and gets back some values, and then requests some more, get back some values. So you have this recursion going on when you converge against a specific identity. That is not yet modeled in the system, in the cluster of all the components when you add them together. So there's bound to be a bug or two in there. I'm pretty sure. Whenever I do this, there's bugs in there. So that is not yet safe. I found something between 10 and 20 bugs when I did this on the code, and some of them were of the kind where you have to. It's 1 in a million kinds of bugs. It's something that happens very rarely, but still will happen at a certain point for somebody. So I'd say it works. You find some bugs which are very unlikely to be found by unit tests. So yes, and finally, everything is open source, so you can just go there and look up the code if you want. So everything is there, including the whole model. The component model it uses is, I think it's the largest one outside commercial places. So it's the largest open source component model for Erlang Quick Check that is out there. Yes. So are there any questions? Or are people destroyed? Yes, Hannes? No, it's not. The commercial quick check I use is not open source, and that's a problem. And the reason is that the reason I use it is because I couldn't do this without it. Yes, it's yes. But it's worse than that, because the stateful model is not really what I use here. I use component models, which is an entirely different thing. So they built stateful models, then they did parallel stateful models, which is another thing by itself. But then what they started doing are these component models, which are really based on a very clever monad, where you can do all this mocking and call out stuff and blocking and unblocking. And there's a whole DSL for writing mock specification where you can say, well, I have these 3 possible calls and they can happen in any order. Or if I commit to this path, then these 3 things must happen in that order. But if I commit to that part, well, then these things must happen in that order, and this call is optional. So you have all these kinds of DSL for describing mocking, and that's very, very powerful. And that is not open source either. And the clustering features that I use are not open source either. So that is a weakness. I think the stateful part is pretty easy to write. I think we could say we take OCaml and we say we want to implement that for OCaml. I think that is not that hard to actually get right. The other thing that is subtle but hard to get right in these quick check models are the generators and the stringers. So what defines their power is really not how featureful they are. It is how good they are at the heuristics, right? Because I've seen examples of using quick check models where you're running a million test cases, it finds nothing because it's just doing pure randomness. This system is not doing randomness, it's doing highly skewed distributions where it targets very specific kinds of things that are very often wrong in systems. So it might take, I have an example where it took 1,000 test cases to find something with one of the competing quick check implementations. This particular implementation found it in 24 cases. So there's really, if you do this right, there's really something to be gained. There's actually really good papers about it. If you have the ACM library available, then they're really, otherwise you have a wall. Yes, but I can link you to the papers. They're all documented pretty well, and it is possible to steal this and implement it if you want. And I think that the papers are reasonably good. A lot of this is not used much outside QWIC, who writes Erlang Quick Check actually. So I tend to be the first user, and then I have to improve the documentation and ask them dumb questions about how do you use this. And there has been, for instance, for the clustering thing in this, I asked them, why is this not working as I expect? And the answer was, oh, but the documentation is wrong. So it's clear you cannot use that. We have to fix the documentation first. So more work is needed. But it's when you look at how powerful it is, we want this in more languages. Definitely, it's so powerful. And then it's fun. That's another thing. It's really fun to hack these kinds of things. Yes. More questions?
Yes.
Oh, come on.
I was just thinking how you handle the pureness with the timestamps. I would just like to ask you how you handle cache or memorization, because if you provide a new timestamp every single time,
Uh-huh.
it's very difficult for you for doing some kind of caching or memorization, right? Because it will always be a new call. So how will you handle that if you have any thoughts on this?
So you think in production or you think in testing here? What is your concern?
Yeah, because I was thinking
Your concern is efficiency.
no, so I was just thinking to reuse exactly that pattern in production. So
Uh-huh.
if I feed every single time a new type, then
Yes.
for me it's almost impossible to do memorization.
Yeah, but perhaps you could decouple it. I mean, most of the time when time passes, right? So time advances, there's nothing to do, right? So if you decouple the memorization from the time, so you say, okay, so I move ahead to this point and there's still nothing to do. Well, then I don't think you need to memorize, because that is a very cheap operation. So I would definitely, if I had that problem and I was in kind of like an efficiency, I worried about efficiency of this, and namely memorization and caching, I would definitely think about, can I decouple the memo cache part from the timing part, such that I can avoid this problem, right? Because you're right, if the timing part is part of your underlying call, then the problem is that this is going to change all the time, and then my memo cache is dead, right? Because it'll be trashed by doing this. But if you, for instance, think about it and say, okay, so first I'm going to take this thing, I'm going to take other parameters, then I'm going to do a computation, is there anything to do, right? If there's something to do, now I have a list of operations. And perhaps that is memorizable or cacheable, or subsystems of that is memorizable and cacheable. And I think nowadays that doing pure computation on the CPU has zero cost. If the problem very often is that you hit some I/O or memory barrier, but doing things inside the CPU to figure out stuff is almost free. So that would be my guess at how I would go about it. Simply try to mod out the time from your memorized calls. If it's possible. I mean, you might be in a situation where it's not. So, yes.
Another technical question. So you have your state M0 and your command C0.
Yes.
Where do you define who defines what C0 might be?
So,
You
yes.
actually write the potential state transition for the
So what
M0?
yeah, so what you do is you say, you define a set of possible commands, right? So the possible C0s are defined by you, right? Each C has a precondition tied to it, which says whether or not it can fire in the current state, right? So given M0, it might be impossible to fire this particular command because it might be quenched at this point, right? Then there's a waiting function that says, I prefer to generate, in this state, I prefer to generate these commands and not that. And that is important. For instance, say I have a timer hanging in the timer system, and I really want that to fire as soon as I can. So I have a wait on that. I say, if there's a timer awaiting and that can fire, up the chance of that firing a little bit. Not a lot, because I want to have these nasty interleavings with timers, but up it a little bit so it is more likely to fire eventually kind of close to this point. And once you have kind of picked a command, then you pick and try to generate inputs for that command, right? And those are also based on the state. So the state can also limit those. And then once you have generated that, you have another precondition that says, okay, so that command with these particular inputs, is that allowed? And if that fails, you backtrack and try other inputs until you hit it, right? And once you have a valid command generated, then you use your transition to figure out what M1 is. And now you are in M1, you repeat the game, right? Another point that I kind of glean over here is that the callout thing nowadays contains both the state transitions, the expected post-condition return values, internal assertions on the model, and external assertions on the system under test. So nowadays, essentially, the callout sequence, that monad that runs that, encompasses all of this transition stuff inside it. That is not true in the earlier stateful models. This is a kind of like a newish development in the last 2 years. But it is more efficient because it allows you to kind of like cram everything into one call out sequence. And the fact that you can have one of the things I didn't really touch on is that you can have several internal model transitions before you have a state transition in the real system. So you might have this ability to do local transitions and then do a new command. And that is what you use the call out stuff for. And it's powerful because it means that you can do stuff like, okay, so the client here, I'm going to add the client to the blocking list and then I'm going to block it. So now, from now on, I know that this client is blocked and I know its process identifier. So when I do an unblock, I can see unblock this process identifier and then continue with remove it from the blocked state and then continue. And this is where the continuations happen. Because I write that as add, block, remove. But what happens in the system is it says add, oh, there's a block, so remove and the rest of the things goes onto the continuation thing over here. And then when the unblock hits, I do this by splicing it into my current state. That is how it works. And you need this in order to handle this because there's blocking calls in here. Yes. Cool. No more questions?